Such as the kid, of course. Yeah, we should. What it is. Yeah. Oh, gosh. Huh? Wait. الشغل خلاص الشغل عند الطريق الشغل مش كده والدرجة هذا شكله الاتصال موجود تعب بس كده لا اللي كانت مش نستوعب تقرأ تصدي معك لا عندي وصل ازاي صوت الهواء ويرحم عياله بس صح 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 بعد الناس 40 سنين أفضل ناس هذا الصراحة اشتغلنا كثير اشتغلنا كثير مش كويس خارج أنا تعال ثاني يوم مش ثاني يوم والله هذا كذا نحاول على ماشي. ليش؟ مثلا بنبدل الموضوع. سيجار لو جيت تحديد أقول لك أنا بره ايش يحصل؟ محمد ولا محمد ولا محمد خدت الحوار. هاي الشيء هذا سويت حاجة جديدة عند الأولاد هاي الأولاد مش لا. والله ما درت محمد بلا مول في الوقت المسؤول هي هاي تعرف دخلت الرسمية ايش 15 20 هذه هذه شيء تتكلم هاي دكتور ايش اللي حصل؟ Oops. مش هو تكساس تكساس صراحة تكساس والله فاهم لو انت عايش ليها بس انا سكيورتي ضخمة فلوس
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today?
I'm good.
Good to hear. All right, today's an exciting day. So it's another ANSYS day. So first announcement, there was a little bit of a mix-up. So even though the due date here says it's Thursday, next Thursday, I did push it back to Friday. So you guys have until Valentine's Day to get this done. So I corrected it on Canvas, but I haven't corrected the document just yet. But I'll do that once I get back to my office. Okay. Okay, and so the subject for today's ANSYS activity is going to be a bike crank. And so if you're not familiar with the bike crank, probably you've ridden a bike at some point in your life. The bike crank is basically what connects the pedal to the rest of the bike assembly. So it's kind of this like basically a little bit of rod. There's slots here for it to connect to the bike and a slot to connect to the pedal. And basically you're going to be applying force on this bike crank with your foot. Okay. And so the scenario that I'm having you guys take on in this activity is from a designer's point of view. So let's say that you work for a bike manufacturing or bike design company, and this design for a bike crank, the pedal crank has been proposed, and you want to run some simulations to make sure that it is good. Okay. So the last few lectures that we've been doing based on our review of strength of materials in terms of the yield strength and the stress thresholds. That's going to play a role today because that's what you're going to use. That's the criteria you're going to use to determine if this bike crank is going to fail or not. Okay. This is also our first 3D ANSYS activity, and so we'll be working in 3D today. We'll be importing a part, so we won't have to do it. We won't have to draw the part ourselves, so that'll save us quite a bit of time. And we're going to be changing materials. Okay. And compared to the first activity, so first activity with ANSYS, I kind of I kind of walked you through every step, every kind of button press, through ANSYS. So today I'm taking the training wheels off a little bit, pun intended, and I'm going to let you kind of do a lot of that stuff on your own, okay? Because we've had a lecture last time on meshing, and so you should be better equipped today to mesh your model, and I'm going to let you apply the boundary conditions with some constraints as well, okay? All right, so if you haven't done so already, go ahead and open up ANSYS Workbench, just because it takes a couple minutes to do so, okay? And then, we'll kind of go through, probably for the first 30-40 minutes, we'll go through kind of the stuff together. And then for the rest of the class, you'll have time to work on the rest of it. Okay, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So while Workbench is opening up, let's go ahead and download the part. And so if you go to the Canvas site and you click on the activity page for activity 2, you'll see that you can download the PDF for the activity. And so that's what I'll be referencing today. But you're also going to need the CAD files as well. right? So for all the rest of the activities, including today, I'm going to be providing you the CAD file for the simulations, okay? So no longer are we going to have to draw out the parts. We may modify the geometries in a future activity, so that is activity 4. But for a lot of the activities, it's just, you're just going to download the part and then load it up into ANSYS, okay? All right, so for the first part of the activity, we're going to be making use of this crank assembly here. Okay, so go ahead and download that. I think I already have it downloaded because of this. I've done this activity so many times now. Okay, so it should be an x_t file, which is what's called a parasolid file. Okay, so actually, let me rename this so it's all one word. You shouldn't have to rename it because for you guys, it should be the first file that you're downloading. Okay. All right, and then after you've downloaded the part, make sure you kind of make note of where it is, either in the downloads folder or the desktop. Let's come back to ANSYS here, okay? Just like we did with the first activity, let's go ahead and load in a static structural analysis. So let's take static structural and click and drag that to the main working area here. Okay, so that's going to open up this window here. And let's import the geometry. So to import a CAD file, you're going to right-click on geometry here, okay? And then you're going to scroll down on the menu to import. Okay. Now for mine, I have a few here just because I've done ANSYS activities in this exact room on this exact computer more times than I can count. But for you guys, probably you're going to have to browse for it. So click Browse, okay? And then you're going to load in that crank assembly that you just downloaded from. Okay, so it should load pretty much automatically. And so if it all went well, you should see a little green check mark next to geometry here. Okay. The symbol next to geometry should change to a P as well. So that's just to indicate the file format. So the P stands for parasolid, which is a file format that's often used by ANSYS. Okay. By the way, if just for those of you who are interested in using ANSYS for your own personal projects or work projects or research, it is possible to take SolidWorks parts and import them into ANSYS. In fact, that's probably the most common way to use it. But ANSYS itself can't load in a SolidWorks file format. And so if you're going to use a SolidWorks file and you want to import that into ANSYS, you have to convert the part into a what's called a common file type. Okay. So in SolidWorks, if you have an assembly loaded, or say you have a part loaded, and say you want to perform the analysis in ANSYS, basically you would go within SolidWorks, you would do Save As, and then you would save as one of the common file formats. So you can use a parasolid file format. So that's the one we're using today. So that's .x_t. That's my personal favorite one, just because it's a parametric file format, so it retains basically all the information for you. Okay. Another common one that's used is IGS. So that's either IGS or .iges. Okay, so they both work. Okay. Another common one is a step file, so that's .stp. Or .step. Okay. So I would say those are probably the most common file formats that you're going to convert to. Okay, and this goes for other CAD software as well. So let's say you're using CATIA or using maybe Autodesk to produce a CAD file. If you want to import it into ANSYS, you would first have to convert to one of these file formats. Okay. So that has nothing to do with the activity today, but I just thought I would mention it just because people are usually curious. Okay, so let's go ahead and let me clear these drawings. Okay, and so if everything worked out okay, you should see a green check mark next to geometry. So everyone is able to import the geometry. Okay. Okay, good. All right, so that kind of skips a whole step for us. So we don't need to actually draw in any geometry today, which is nice. Okay, so one other thing that we're going to do before we actually start with the analysis is we're going to create a custom material. Okay, so if you go back to the PDF for the activity, you'll see that the material that we're using today is called aluminum 6061 T6. Okay, and this has a Young's modulus of 1 × 10⁷ psi. and a Poisson's ratio of 0.33. Okay. So this is not one of the default materials that are available within ANSYS. So we're going to go ahead and add this material in manually just so we can use it in our analysis. Okay. Okay, so to add a custom material property, you're going to go to engineering data here. Okay. So you're going to double click on engineering data. Okay. So that's going to open up a new window. Okay. So it's going to show you all the materials that you have loaded into the job already. So right now we only have one material that's loaded, which is structural steel. So let's go ahead and add a new material. So for today, I'm going to show you how to add a material from scratch. And so, if you just to show you how to manually add the materials yourself, there is a material library within ANSYS. We will make use of that in future activities. But for today, since we're going through the trouble to add a material, I'm just going to show you how to make one from scratch. Okay. Okay, so to add a new material, you're going to click on this box. You're going to give your new material a name. Okay, so I'm going to name my material aluminum 6061. Okay. But in theory, you can name the material whatever you want. So you can name the material Bob if you want, as long as you remember what material properties Bob has. Okay. Okay, and then now we need to add in its Poisson's ratio and Young's modulus. Okay. So to do that, we're going to make use of the material toolbox here, kind of on the left-hand side. So we have to define what kind of material this is. So by default, probably you're going to have this this menu kind of expanded here for linear elastic. Okay. So that's probably the simplest material that you can probably make for a structural simulation. Okay. And we're going to use isotropic elasticity. But you can see here that there's lots of other properties that you can add here too. So you can add things like density, melting temperature. If you have a hyperelastic material, you can add some kind of hyperelastic model here, right? So we have a lot of hyperelastic models. We'll go over this, or at least kind of, briefly kind of later on. But for today, we're just going to use kind of the simplest material model, which is an isotropic linear elastic material. Okay. So under linear elastic, you're going to click and drag isotropic elasticity, and you're going to drag that on top of your new material that you just created. Okay. Okay. And so after you click and drag that down there, you're going to see that you're going to have a new entries down here. Right? And there are going to be two windows here that are highlighted. So you're going to have one window for the Young's modulus, right? You can see that is highlighted yellow, so that's telling us that we need to input something there. And then we're going to have a highlighted for the Poisson's ratio as well. Okay, so we need to add both of these material properties in order to fully define our material. Okay. All right, so let's go back to the document. And so we can see here that our Young's modulus for this material is 1E7 psi. Okay, so let's go ahead and add that in. Now, when you're adding properties with certain units, you want to make sure that you get the units correct. Otherwise, your material properties are going to be off. Okay. So by default, you can see that ANSYS uses SI units. Okay. So the default unit for the Young's modulus right now is Pascal. And so, but the Young's modulus that was given to us in the specifications is actually in PSI. So we need to change this the units here to PSI. So go ahead and click on this drop-down menu and switch this over to PSI, okay, before you enter in. Okay. Then let's enter the value here. So luckily, ANSYS does recognize scientific notation, so we can do 1E7. Okay, hit enter, and then that will define the Young's modulus for units. And then for the Poisson's ratio, there's no units for that, so we don't have to worry about that. So Poisson's ratio is 0.3. We'll just punch that in. Okay, and then after you enter in the Young's modulus and the Poisson's ratio, you can see that the bulk modulus and the shear modulus have already kind of automatically populated. That's because for a linear isotropic material, there are formulas that we can use to compute the shear modulus and the bulk modulus, which depend on the Young's modulus and the Poisson's ratio. So, those should kind of automatically populate for you. Okay, but the most important ones is that you have the Young's modulus in PSI and the Poisson's ratio at 0.3. All right, any questions on that? Okay, good. Okay, so once you're done with that, let's go ahead and close this out. So there's a tab view up here. So go ahead and close the tab for engineering data. Okay. Now we're ready to start ANSYS mechanical, which is where we're going to do most of our analysis. Okay. So just like in activity 1, let's go ahead and double click on model here. That's going to open up ANSYS mechanical after about a minute or two delay. Give it a second. Usually slow today. Really slow today. All right, there we go. Hopefully your guys loaded a little bit faster than mine. Okay. Okay, so if you did your geometry import successfully, then your part should be loaded in here. Okay. Just to go over the mouse controls really quickly, just because you're going to be zooming around this a lot. The middle click is your best friend to kind of rotate around. And so to rotate around the part, you're going to hold middle click on your mouse. Okay. And so holding middle click on your mouse and moving around let you rotate around the part. Okay. If you want to pan to the left and to right, or to pan up and down, the way to do that is to hold Control on your keyboard and you can click on the middle click. Okay. That'll let you pan around just like that. I think we went over this in the first activity, but it's good to kind of remind ourselves too. Okay. And so with that, you should be able to rotate and move to any kind of position that you. Okay. All right. So let's look at our part here. So you can see that we've loaded our bike crank assembly, but if you compare to the image on the document here, there's some extra parts. And the reason for that is because we've loaded in an assembly of different parts. Okay. So a lot of times, when you create a model in SolidWorks or in CAD, usually it's an assembly of different parts kind of merged together into one. Okay. And so for this particular case, we actually have 3 parts that are part of our assembly. Okay. So the reason you do this, in CAD, the reason you do this is to, basically make sure that, if you're going to assign different properties, or usually it's because it's easier to just kind of construct different parts kind of piece by piece like this. Okay. The nice thing about ANSYS is that it actually loads in all the different parts in your assembly kind of all together like this. Okay. All right. So first thing we're going to do is I'm going to show you how to suppress different parts in an assembly. Okay. Because oftentimes, when you load in a whole assembly like this, you actually don't need, or you actually don't want all the different parts in the assembly. Okay. For this particular activity, it doesn't matter all too much. We could probably keep all the parts, but our tutorial on how to deal with assemblies is actually the next one, activity 3. So, so for now, let's go ahead and suppress all the parts that we don't need. Okay. So basically, a suppression just means that we're going to take this part and just remove it from the analysis. Okay. So for instance, we don't need this pedal part right here. So let's go ahead and suppress it. So to suppress a part, you're going to go under geometry right here. Okay. You're going to right click on the part that you don't want. And then there should be a part here, or there should be an option to suppress this body. Okay. So if you click this, it's going to suppress it. So let's go ahead and get rid of that. And so by suppressing the pedal, it just removed it from the assembly. And then let's also get rid of this little kind of connecting part right here as well. So let's go to right click this and suppress this body here. Okay. So then all we're left with is just the bike crank itself. Now suppressing is different than hiding. And so, let me unsuppress this one just so you can see. Okay. And so it is possible to hide the body. Okay. But hiding doesn't actually remove it from the analysis. So hiding, all that does is just make it, turn it invisible, but it's still going to be part of the analysis. So you don't want to hide. You just want to suppress it instead. So make sure you click suppress. Okay. Any questions on suppressing parts in the assembly? No good. Okay. All right, next thing we're going to go over is how to assign different materials. Okay, so like I just mentioned, a good reason why you want to do an assembly of parts is so that you can assign different properties or different materials to each part in your assembly. Okay. So remember earlier we defined that aluminum 6061. Let's go ahead and assign that to our bike crank. Okay. So go ahead and left click on bike crank, and then in the bottom left of the screen, you're going to see that there is an option for material assignment. Okay. All right. So right now it's assigned to a material property of structural steel, which is the default. But let's go ahead and change this to the aluminum material that we just created. So click on this arrow here, and then go ahead and click on aluminum 6061. All right, you want to make sure that you do that, otherwise your results are not going to come out correct. Okay. Okay, good. All right, so we've loaded in the part here, we've suppressed the parts that we don't need. We've assigned the materials. Next step is the meshing. So this part, I'm going to let you guys kind of tinker with yourself. Okay? We just had a lecture on meshing on Tuesday, so now it's kind of the time to apply it. Okay. So let's look and see what a default mesh looks like first. So let's right click on mesh here. Let's click on generate mesh. Okay. So that's going to create kind of a default mesh for you. Okay. But I can tell you right away that this mesh here is not very good. So it's a very coarse mesh. Okay, so you can see the elements are pretty huge here, right? So I want you guys to do better than this mesh here. Okay, so in particular, let's assign both the size of the elements as well as the order and shape of the elements. So if you remember from activity 1, the way that we're going to do this is we're going to right click on mesh. We're going to click on sizing. Okay. So that's going to allow us to assign the size of the elements in the mesh. Okay. You want to make sure you select the entire body here. And so if you're not able to select the whole body, click on body here and click on that. Okay. All right. So I want you guys to assign a mesh size. And the other thing I want you guys to assign is the method for the mesh. So the method is going to allow you to assign the element order as well as the element shape. Okay. So go ahead and create a method object. Once again, select the entire bike crank part here, click apply. Okay. And then from this, you can go ahead and select the method as well as the element order. Okay. So the method is going to allow you to change the shape. Okay. So since this is a 3D part, you can basically choose between tetrahedrons and hexahedrons. Okay. So on Tuesday, we went over the pros and cons of those two shapes. Okay. And then for element order, you can choose either linear or quadratic. Okay. So I'll give you guys about 5 minutes. It probably shouldn't take you guys too long to kind of experiment with this. And so try different sizes, try different, element orders, try different shapes. And then, I want you guys to arrive on a mesh that you feel kind of good about. Okay. All right, I'll give you guys 5 minutes. I need to take a break for talking for a second. We'll come back in about 5:57. If you have questions, just raise your hand.
So it's under 5 millimeter.
Yeah.
Entire body.
Oh, you need to select the geometry for this. So with the click on, yeah, so you're good right there. And click on right here. And then click apply. Yeah, so every mesh object, you have to assign what part of the object it is. That was pretty good. Yeah, so you're able to get a hex mesh, which is good. And one thing, actually, go back, click on mesh. One thing I actually look for a lot is, you notice, if you're looking at the part in this direction, you see that there's kind of 2 layers of elements. So that's actually pretty good. So that's one thing that I look at for these kind of meshes. Yeah. Good.
Yes.
You read so this.
No, no, I'm not gonna.
Yeah. What's up? Yeah. Yeah, so you should, so that looks pretty decent already, so that looks pretty good. Yeah, so what I was telling him, so, we'll go over this in the future, but if you look, you kind of look at kind of this direction. You'll see that there's kind of two elements that are through the thing. So that's usually a pretty good sign that you have a good relationship. Because if you remember from the default mesh, I took it all, but there's only kind of one element here, so that's usually. So you usually want to choose the size small enough so you have multiple elements.
Are you working with?
Oh, I see.
Yeah, it's good.
One, so. One of them.
Yeah.
So I was trying to do the default settings, just to get a grasp of what's going on. See if we can like.
Oh, so to run the simulation, you actually need to apply modes and constraints on it. So right now, we're only looking at the, yeah, we're gonna do modes and constraints. That's just.
That one, I was like, why it's not showing?
Oh, yeah.
Yeah. Yes. That's what.
What's the number here?
About from the fire. Oh, it's fine. It's probably gonna work. The limit is 16,000.
Okay, so you guys should be just about done. Hope you guys play around with the size a little bit so you can see kind of the effect. Of different mesh sizes, but let me go ahead and get a mesh just so I can kind of catch up to you guys. Okay. All right, so I saw a lot of you went for a hex dominant mesh, which is good. If you're using a tetrahedral mesh, it's not, again, there's nothing wrong with tetrahedrons. It's just if you can get a hex mesh, then that's usually a little bit better. Okay. So one thing I've been telling people, going around, one thing for a relatively slender element or relatively slender part like this is that one good kind of metric for your mesh quality is to make sure you have more than one element through the thickness. Okay, so if you look at kind of let me zoom in actually. So if you look at kind of this part of the part right here, okay, you can see that if we're going across kind of the shortest distance across the bike rank, we cross two elements there. So that's usually a pretty good sign that your mesh size is usually small enough. Okay, we'll go over the reasons for that a bit later in the semester once we start talking about shell and beam elements. But that's usually a pretty good indicator for your. Okay. All right. So that is the mesh right there. Remember, for a structural simulation, you want to use quadratic order, just to avoid just because you can in ANSYS and just because it's there's no reason not to use quadratic in this case. Okay. Okay. So the next part of the activity is we're going to apply loads and constraints. So our loading for this part is actually quite simple, just like the previous activity. Okay. So we're going to have one force load and one constraint. Okay. So to kind of remind you how to apply a fixed constraint, let's go ahead and right click on solution A5, go to insert, go to fixed support. Okay. And so just to kind of remind you of fixed support, basically you're going to indicate which parts of your model are going to be, fixed to something. So that means it's not going to move or rotate or kind of translate or anything like that. Okay. So we're going to need one of those. Okay. And the other thing that we're going to need in this activity is a force. Okay. So last time I know we used pressure, just because that's just how that activity is formatted. But for this case, it's a little bit more natural to use a force load. Let's go ahead and add a force. Okay. And I want you guys to determine where is best, first of all, where is best to apply these two boundary conditions. Okay, so where to apply the fixed support, where to apply the force. And then in particular, for the force, I want you to determine what makes sense for the direction of the force. Okay. So the only constraint that I have is that the force must have a magnitude of 100 pounds. Okay, I'll get a stylus for this computer so it's not so I don't look like I'm writing serial killer writing on the screen. Okay, so the magnitude of the force has to be 100, but whichever direction that you choose for the force is going to be up to you. So you can choose to apply the force in the Y direction, in the X direction, in the Z direction. Okay. So I'll let you guys choose. So here's a scenario that I want you guys to think about when you're choosing these boundary conditions, right? So whenever you're doing failure testing, so you're doing FEA and you want to find out if your part is going to fail or not. Okay. Usually the way that you usually do this is you simulate what's called the worst case scenario, right? So basically you're going to put this bike crank in a scenario that makes it most likely to break. Okay. And there's a particular direction where you can apply the force, which is going to cause the most stress. Okay. So for this next part right here, I want you guys to do a little bit of experimentation and change the direction of the force and find out, which direction of the force causes the most stress in your part. Okay. Let me give you guys a little bit more context, right? And so, remember, this represents the bike crank. And so this part of the bike crank right here is going to be the one that attaches to the bike frame. Okay, so the bike chain attaches here. So this is where the frame attaches. And then if you remember, from the parts that we suppressed, this part of the bike crank is where the pedal attaches. Okay. Now, I'm going to tell you where the force is applied. So the force is going to be applied at the pedal, right? And so we're going to simulate a case where someone is kind of pushing down with their foot. Okay. So the location of where we're going to apply the force is at the pedal. Okay. You can choose any of these interior faces here. And we're going to look at a situation, remember, worst case scenario. So worst case scenario for a bike crank is, let's say that you ran over kind of a stick, and then the stick gets stuck in the wheels, and then your entire bike kind of locks up, freezes up. Okay. And so in those situations, someone's going to be pushing hard down on the pedal, but the pedal is not going to move. But all that force, all that stress is going to be transmitted to the bike crank. Right. So I want you to use that information, decide where you want to apply the fixed support, decide where you want to apply the force, decide the direction of the force, and then experiment with that a little bit to see where which direction is going to cause the most stress. Okay. And remember, to apply a force in a particular direction, the way that I like to do it is if you click on the fourth boundary condition here, you can change the definition to components. Okay. So that way you can apply the individual X, Y, Z components of the force this way. Okay. All right. Remember, the only requirement is that the magnitude of the force be 100 pounds. But it may be that the most dangerous situation is maybe you're applying the force in a diagonal direction. Right? So maybe there's an X and Y component, or maybe there is an X and Z component. Okay. And so, kind of experiment with that a little bit, okay, but also kind of stay realistic. And so if someone's sitting on their bike, realistically, what direction's gonna make the most sense in terms of where they're applying that force, okay? Okay, because remember, we're running a simulation that's meant to represent kind of a realistic scenario. So, try to think about that as you're applying the force, okay? Okay, and then to view your results, let's go ahead and add a couple of results in here. So let's go ahead and right click on solution A6. We're going to add total deformation. That's usually a good one to look at. And then just so that you can analyze your results, let's go ahead and add the equivalent von Mises stress as well. Okay, so again, I'll go ahead and give you guys maybe about 10-15 minutes on this part. So, apply your boundary conditions, the force, location, and force direction. Go ahead and run your simulation and look at the stress, okay? And try out maybe 3 or 4 different force directions. And see kind of which one results in the highest stress. Okay. All right, so I'll give you guys about 15 minutes to work on that. So we'll come back at 6:20. And then we'll kind of talk about it. But if you have questions, just raise your hand. I'll come around you. Yeah, so that's one thing we do. So refinement, that's one of the downsides of refinement. That refinement only works for tests. And so even if you take text down, it's going to transfer. Okay, one of the downsides. Even though I suppress it, if you suppress it, it should turn back to. Or I suppress it. You see here?
Yeah.
See the ones.
No, yeah, actually it is a feed, but then I realized.
Yeah, sometimes.
Not jump on that because I calculated it from all. So it's like sometimes small.
I think what I have.
Also converted.
Now I just.
Yeah. But it did the mesh.
And I thought we had a reinforced by me.
Oh, and I switched to force. I'm really changed the two.
Doesn't select the PSI. Did you do that change?
Yeah.
From EA to PSI?
Yeah. Okay.
Should I? That shouldn't affect.
I wouldn't worry about it. But actually, the way that I actually. Sort of apply, I hope.
Yeah, that's what I'm.
You just make that sign. That person, however.
Oh, like the video that
Yeah, so that tool will actually do it.
31 to find, let the local publics out.
It kind of reflects the mesh, but also consistent. So with this way, we're not adding good. But you still gotta know what you're doing. Yep.
It's not like a thing. That's great. Do you want to this with the this and this how?
Everything should convert on that. Yeah, so like with the mesh sizing and especially the material properties, it should all convert to whatever you're doing. So,
Okay.
so yeah, you should never have to go back and change.
Okay.
Yeah.
See, what I did is support.
Yep.
Because this is gonna be fixed,
Mhm.
right? So. Those three both right here. Oh, we chose this, because that's what's fun.
Yep.
And then,
Yeah, makes sense.
want to make sure.
Yeah, just make sure you try a couple different directions.
Try to look different methods.
We'll keep the back up.
Okay, I
Then
see.
try different directions, see which leads to the highest.
I see, okay.
Yeah.
I'm doing this right. Yeah.
Perfect. So we're looking for the stress here, so, in particular, the maximum magnitude of stress. Sorry. Yeah, that's right. So what's happening when you apply it in Y direction, basically you have like a fixed beam. And you're applying like a bending stress. So bending, if you think about it, if you have kind of like a rod or something, and someone told you to break it in half, right? Most instinctual things do kind of bending things. So bending is kind of the best way to maximize the stress. Because if you try to push it out in the next direction, it's going to be, you're going to be compressing it. It's possible to break something with compression, but you have to apply a lot more force. Z direction, technically that's a bending as well. But that's also kind of not realistic. It's, no one so yeah, so Y direction, that's the best. So you're gonna change this definition. Yeah. So you have to, next slide.
Which first?
Because that's the actual voltage. Because there is a part that comes. That covers this whole.
Yeah, so for this one, yeah, so for this one, this was a meter, so this is our. So I'm viewing it kind of from like this way, yeah. So I think for this one, I think I just did it in one. So the bike itself is kind of in like that.
PSN.
So I think I just divided it into one.
PSN.
I don't know, it shouldn't say PSL. It's information or?
We do metric.
Yes, I have to my vision. You were stressing.
So very special. It's specifically for being a fraud. And so what that's gonna do is that if you apply a force on this one, it's actually it's gonna distribute it to the. So, yeah, so that actually doesn't make more sense. Yeah. Okay. Very much. Yeah.
This doesn't look like it. But it doesn't matter.
So
Not between that one or this.
Um,
I think this is.
But through this one, you consider it the stress.
So I just put.
Yeah.
Oh, we talked. Yeah. I'm gonna get a photo. I don't know, I wonder if
So I don't know if how you put each of that.
300.
So like you're doing this, right? I think.
Well,
That's good. That's good. What the count. See if I can- That'd be cool.
Oh.
So this one. Yeah. Yeah. That's where I don't know. Like it's super.
Everyone on Zoom, you guys doing okay?
Yeah, so far so good. Just had a question. When I mesh with hexahedral elements, it mentions that there's a certain percentage that's still set to be like a pyramid or tetrahedral. Is that fine, or is that an area of concern?
That's fine. It's normally it's actually almost impossible to get a full mesh of all hexahedrons. That's why if you go to the settings, that's why it says hex dominant. So it's going to try to create as much hexes as it can. But there are just some regions, especially around the finer features, where they have to use text. So that there just that it says it's a warning. It's not. It shouldn't really be a warning. But that just tells you how much percentage is not hexes. That's total.
Gotcha. Is there a percentage that we should be wary of, or is that just kind of up to the user discretion?
Yeah, because it depends on the geometry. So there's going to be some geometries where it's going to be much easier to get hexes, like you get just literally like a literal cube. You should get 100% hexes on that one. But the more curved your geometry, the more weird it is. You're going to have a smaller percentage. And for some models, it's going to be impossible to get any hexes on there at all. It's kind of a case by case basis. But usually the measure within ANSYS is pretty good. I actually have a lot of faith in the ANSYS measure, probably more than I should. So I usually have enough faith that the ANSYS did its best to get as much hexes as possible. So
Gotcha. Thank you.
okay, so I know it's not 6:20 yet, but it kind of feels like everyone's kind of gone down this part. So I hope you guys tried out a couple different directions of the force. But the direction of force that actually creates the most stress here is going to be a force in the y direction. So either in the negative y direction or the positive y direction. So the reason for that is because if you put a force in the y direction, you're basically going to be putting this beam into bending. Right? And I'm not going to try it. Bend it. Okay. And so basically the way that to apply the highest amount of stress, or basically the way to break any kind of slender object like this, is to put it in bending. So if you think about it, think about kind of a slender object that you've tried to broken before. So think of like a chocolate bar, right? And so if someone tries to tell you to break a chocolate bar, you're going to put the chocolate bar in kind of a bending kind of mode, because that's the easiest way to kind of break it, right? And so it's the same thing here. So, you know, the direction of force that causes the most stress is going to be in the y direction. Okay. And if you look at the stress here, you can see that that's the case. And you can see most of the stress here is going to be concentrated right around that neck here of the bike frame. Okay. Okay, good. All right, and so that's most of the activity there. And so if you go back to the PDF, okay, we've basically done problems 1, 2, 3, and 4. Okay. Okay. Next, I'm going to let you guys work on problem 5 here. So problem 5, I want you guys to determine what the maximum amount of load that this bike crank can take before it actually breaks. Okay. All right, so in this problem, I tell you that the yield strength of the bike crank, or of the aluminum, I should say, is 35,000 psi. Okay, so what that means is that the equivalent stress in the bar, as long as the equivalent stress stays under 35,000 psi, then your bike crank is going to be good. Okay. So under this default loading, again, you know, this exact number is going to depend on your mesh. So your mesh might be a little bit, you know, a little bit finer, so your number might be different. You can see right now that the maximum stress in my simulation is about 13,290 psi. Okay. If you're not getting the stress values in psi, just make sure you change your units. And so to get psi, it's the very last one right here. So that's US customary with inches, pound mass, pound force, Fahrenheit, seconds, and I don't know what VA is. So, okay. Find my volt and amperes, but so right now we're pretty good. So we're pretty far away from breaking. So even with the 100-pound force, even with the worst case scenario of the bike getting kind of locked up, our bike crank should be able to withstand it. Okay. So with that in mind, you know, I for problem 5, I want you guys to determine what's the maximum amount of force that you can apply before the bike crank actually starts to break or becomes in danger of breaking. Okay. So for this one, I want you to increase the magnitude of the force. Okay. So instead of 100 pounds, you're going to increase this to, you know, minus 120. Okay. Or if you did in the positive direction, that's fine too. So 120, 130. Okay. I want you to increase the load, rerun the simulation. So after you rerun the simulation, the stress should increase if you increase the load. Okay. So you can see here, I've increased the load to 120 pounds. And you can see the maximum stress now is about 15,950 psi. Okay. Okay. So I want you to keep increasing the load and rerun the simulation, right, until it breaks. Okay. But I want you to do this for a factor of safety of 2. Okay. So I don't want you to push it all the way to 35,000 psi. I want you guys to push it up until you reach half of this, right? So remember a couple lectures ago, I think this was about a week ago, we went over the idea of factor of safety. Okay. So with factor of safety, you're going to take the maximum yield strength, which is 35,000. And then you're going to divide that by the factor of safety, which is 2. Okay. And so if you perform this, then the maximum stress that we can withstand, or that we should withstand in our simulation, is 17,500 psi. Okay. So for problem 5, I want you to kind of keep pushing this, increase the force, and try to get the stress as close as you can to 17,500 psi. Okay. And then whatever force that you use to match that number, I want you to report that in your activity report. Okay. You don't have to get 17,500 right on the dot. Okay, that's really hard. So try to get within maybe, you know, if it's 17,000, between maybe 17,250 and 17,750, that's good enough for me. Question, yes.
Please use to PSI and PSF one for my.
Yeah. So for PSI, you're going to go to home under ANSYS mechanical here and go to units, and then you're going to go to the second US customary here. So US customary with inches, everything like that. Yeah. So that should change your stress to PSI. Okay, so anyway, so for problem 5, if you're somewhere between 17,250 and 17,750, That's good for me. So don't try to hit 17,500 exactly. It's gonna take you all night. So as long as you're within that threshold, then that's good for me. Okay. So find the amount of force that causes that stress and then report that in your activity report. Okay. So that's problem 5. So you guys can work on that for today. You should be able to get that from today. Okay. Problem 6, I want you to repeat what you did for problem 5, but I want you to change the direction of the force. So instead of applying the force in bending, I want you to apply the force in compression. So that basically means you're going to change the direction of the force from the y direction to the negative x direction. Okay. And so I want you to change that direction and then again keep increasing the force until you get stress values that are within this range. Okay. What you should see is that in compression, then this bike crank can withstand a lot more force. Okay. That's what you should see. And so keep increasing keep releasing the load until that happens. Okay. All right, problem 7. So problem 7, this is going to be kind of a mainstay of all of our activities from now on. So a big part of this class, or kind of what most of your grade is going to be based on, are going to be the projects. And a big part of that is the writing of the reports. And so to kind of give you guys a little bit of practice, for every activity, I want you to write kind of a 1-page summary of your results. Okay. So a big part of this is you have to communicate results. And so basically, I want you to prepare basically like a brief to your boss. Okay. So imagine your boss has tasked you with doing a stress analysis on this bike crank, and your task, and you need to write a 1-page brief to kind of summarize your result to your boss. Okay. So in this kind of brief report, you should include some information about your FEA modeling decisions. And so things like what you chose for the element size, the element order, the element shape, what you chose for the boundary condition, the directions of the loads. Okay. You should include the stress results. Okay. The maximum load, as well as a recommendation on whether or not to whether you should design a more robust bike crank, or maybe you can make a recommendation to maybe reduce the amount of material to save some material costs. Okay. Your brief should include at least one figure, so make sure you include that figure in that report. Okay. Okay. So this is going to be a recurring theme. So for every activity that we're going to do, just assume that at the end you're going to have to write a report. Okay. A brief one. Okay. And then once you're done with all of that, problem 8 is I want you guys to do another analysis on a full bike frame. Okay. So actually, if you go to the Canvas site, you're going to see that there is a second CAD file that's available for download. Okay. So that CAD file is this bike frame that I've kind of have at the very bottom here. Okay. So for problem 8, you're going to run another analysis, and so you're going to apply load, you're going to apply meshing, and you're going to report on your results. Okay. All right. Any questions on any of this?
So for the second file, do you need another report or just that?
No. So just for the second CAD file, just answer the questions at the bottom. So basically, just show me the deformation and the stress, and there's a couple small questions. Okay, all right, so we have about 18 more minutes left in class. So I'll stick around. If you have any questions, just raise your hand, I'll come around. If you're on Zoom and you have questions, just drop something in the chat. But you guys are free to keep working on this activity until the end, but there is another class at 7, so we do have to get out of here by then. But that's all I have planned for today. So if you guys are heading out, so thank you guys for coming today. I hope you guys enjoyed our second activity, and hope you guys have a good weekend, and I will see you guys on Tuesday.
Thank you very much, Professor.
Okay, it's good. Okay.
But when you say that this is the most.
Yeah, because the material will actually review. You apply the force that way, the thinnest part of the material is just gonna be like standing. It's not gonna be like shear stress. It's not gonna be on the maximum shear stress. It's not gonna fracture. It's gonna fall. Maybe it can fall more, but It's not gonna catch it. We'll see, I don't know. If you apply to the.
But he said that this was the policy. I'm asking for more.
Move file over, it's gonna work, right?
Yeah, you have to compress it though, you have to archive it. Yeah, so if you archive it, then you should be able to move it back.
I don't follow the set here, but my direction was the not sure.
Yeah.
I think the Z direction. I got this one way far.
Yeah, so Z direction also pushes the bike crank in, but it's also kind of not realistic because, you know, people are pushing down the bike crank, but to apply a force in Z direction, you have to.
I feel like this scenario would be like a.
Yeah, that could be a possibility too. Yeah, so that technically is true, but, so yeah, you can use Z direction.
You said a typo.
I get it. Thank you.
And also put a first one. We have to. I'm just saying that, we got out.
You have to apply that for.
Like exactly, like, it's exactly. That's what it's.
The one thing.
How do you archive it?
Yeah. You're gonna read it.
You are part for the one. Go to file. Archive.
You're gonna take $5. So you think you left it? It might be.
Oh, see, Professor.
You guys, have a good weekend.
I was like, oh, yeah. Huh? Oh, yeah. So the second class, I was just listening to her and I was like, oh. And then we're only the only last one.
So cylindrical support's not necessary for this one. We're basically treating it as like a pseudostatic simulation, so we're just applying the fixed.
I want to wear this. We tried with them.
Yeah, cylindrical support is more for dynamics, which we'll cover a little bit later on in the class, but dynamics are also a little bit hard to. Have a good weekend, guys. One on right now. Yeah, so wherever you use some of this, so this is. So for this part, it's probably managed to, ultimately not. So whether you select. Something you just select it in that mode. No, do it then. Okay, so everything. So then, yeah. So I can help. Here. By the word. What you're saying. You know, yeah, you know, like. Go to the bottom. Right now, the contract that. And you did it, you said that. Okay, so yeah, that part, that's tough on there, is intentions. Action.
You see that?
But backwards, so that should. Which means the negative sign does show that this is pressure. Quickly, I will play actually to the number.
So I usually expect it.
Yeah, but I guess it it says now
We try my.
do not choose to.
Probably have to do some.
Some problem now?
We think about.
You know, I think it's like how you check the regulations. Then I keep the business provided the system.
No, yeah, by number of elements means your size messes. So change the mesh size and that affects the number of elements. We don't like manually enter the number of elements. Yeah.
I guess the question.
Yeah.
Should be facing the direction of the. So, yeah.
That's really just tensile stress. If we try to load in insert stress, go to minimum. Usually when I think of maximum minimum, I'm thinking max, it might be actually just going high. So see for this one, this shows the compressive stress on the bottom. This might just be showing the tensile stresses. Another one that you can do is you write the coaching stress, coaching normal stress. That's probably the one that you both think. You can see the magnitude go up or down, tensile and compressive. Yeah, they might have changed the definition of maximum flexibility. Just the value itself should be. I mean, what I think of magnitude. Right.
There, we try to save money.
Oh, where did you save the project?
Obviously.
Should be fine. Oh, I see activity 2. So you can't even save the project itself. Oh, okay.
It's like,
Yeah, maybe try saving it to the local files. Save it to the local files and then archive it and put that one in your. Yeah. They like documents.
I know you could check the skewness in ANSYS. I think you just closed it, but I was wondering if where that would be found in the Windows.
Yeah, so to check speeds. Okay, yeah, so check skewness, you would go under quality and go under mesh metric. So this will kind of show you the skewness of the function. So, so the skewness metric that we went over last time, it's basically varies between 0 and 1, 1 being bad and 0 being good. So this mesh has an average skewness of about 0.38, which is really good, which is not surprising because this geometry is pretty simple. The max skewness, this almost always happens. There's usually at least one element here which has a tremendous skewness, but that's usually on the middle. So you can have that high, no problem. It's usually the average that I look at. And this right here is a histogram that for mesh quality. Yeah, so you want to have most of your elements be kind of on this left side of the histogram.
Gotcha. Thank you.
All right, so we're out of time. So I think next instructor was here. Saw him. So all right, have a good weekend, everybody.